In the last lecture, we looked at multidimensional finite volume methods based on dimensional splitting. And in this lecture, we'll look at more fully multidimensional finite volume methods where we compute fluxes or use a wave propagation sort of approach to update the cell based on solving problems in both the x and y direction within a single step. So we'll first look at how basic flux differencing conservative method in 2 dimensions is derived from the integral form of the conservation law, and then look a bit at scalar advection first, and then look at the generalization to a general system of equations and the idea of a transverse Riemann solver that can be used to bring in some more multidimensional information. So if you recall from the derivation of a conservation law in 2 dimensions, the conservation law came from this integral form of the conservation law where the total mass of Q in some region omega changes only due to fluxes around the boundary. And if we assume that this vector flux function f dotted with the outward pointing normal gives the flux across the boundary at each point, then we have this conservation law. And in the case where everything was nice and smooth, we can manipulate this to get the standard PDE form of the hyperbolic equation. But instead, what we want to look at now is applying this to the special case where omega is a rectangular grid cell on a Cartesian grid, although it could be applied on other sorts of grids, but we'll look at the Cartesian grid case here, in which case if we have a grid cell and our Qij now is some cell average over this grid cell, so Qij at time n is some approximation to 1 over delta x times delta y times the double integral of Q over this particular grid cell, then when we apply this integral of the outward pointing normal, integrating that around the cell, then this inner product of the normal with the flux vector results in the flux f at the left and right boundary. Well, since the flux is sort of in the outward direction, it would be minus f at the right boundary and plus f at the left boundary. And similarly, at the top and bottom boundaries, the outward pointing flux is either g or minus g. And then integrating around the boundary, the outward pointing normal, we end up with this expression, which suggests that if this integral is like delta x times delta y times the cell average, then the derivative of the integral here is an approximation to this difference between time n plus 1 and time n of delta x delta y times the cell average, and the fluxes on the right-hand side, each one of them we could approximate with some numerical flux function. So for example, at the right edge, at x I plus a half and y y going between yj minus a half and yj plus a half as we integrate along the left or along the right side of the cell, that integral we could approximate with this numerical flux at the right edge of the cell. Similarly, this flux we would approximate with some numerical flux at the left edge, and then at the top and the bottom we'd have approximations to these two integrals. So that's the same formula again, and that means that our fluxes fi minus a half should be some approximation to the integral of the flux along the edge that we're integrating on, which would be a vertical edge at the left or right, at the left edge of the cell, in this case at I minus a half, and then also integrated in time from Tn to Tn plus 1, and then normalized by dividing by delta t and delta y, so it's an approximation to the flux. And similarly at the top and bottom boundaries, we have g fluxes that come from integrating g along the top or the bottom edge of the cell. And if we just take this formula at the top and divide by delta x and delta y, then we get the standard flux differencing form of a finite volume method, which is a very natural generalization of the one-dimensional finite volume method to now include fluxes in the y direction as well as those in the x direction. So comparing this to the dimensional splitting that we talked about in the last lecture, remember one way of solving the multidimensional problem was to do dimensional splitting, where we start by ignoring the y derivatives altogether and just update from Qn to a flux differencing based on values at time n in the x direction, and that gives us some intermediate value Qij star. And then once we've gone and done sweeps across every row of grid cells and updated everywhere using the equation in the x direction, then we can go ahead and ignore these terms and solve qt plus g of qy equals 0 in the y direction. So now we'd be using q star as our data, so we'd be updating q star, and these fluxes g star at j plus a half and j minus a half would be based on the intermediate data that we computed there. By contrast, the unsplit method that we were just looking at, we would update Qijn by using fluxes in the x direction based on the data at time n, and also using fluxes in the y direction based on the same data Qn, rather than using some intermediate value. So if we're thinking of it in terms of solving Riemann problems, in the split method, we'd be solving Riemann problems based on the original data in the x direction, but then we would update the cell averages before using it to solve Riemann problems in the y direction. Whereas in the unsplit method, we'd be solving both sets of Riemann problems based on the data Qn. And we saw in the dimensional split case that we could, by doing this splitting, we were also sort of bringing in some cross-derivative information. In the case of the unsplit method, we'll have to bring that in more explicitly. So the sort of method I will be talking about is this fluctuation form together with high resolution correction terms. And so if you remember, in one space dimension, we had a method that looked like this, say in one dimension, where our updating formula involved these fluctuations that corresponded to waves coming into the cell from the left or the right edges based on solving Riemann problems at those edges. And then we also had some correction fluxes in the x direction, these f tildes, which were defined at the left and the right boundary. And in that case, those correction fluxes were bringing in approximations to the second derivative in the x direction, with some limiters typically applied to avoid oscillations. And now we're going to do something similar in the y direction, so we'll bring in also the differencing in the y direction, which in fluctuation form means that we are now looking at, clear this, we're now, in order to do things in the y direction, we'll be looking at fluctuations in the y direction, which correspond again to the waves that are coming into the cell from the interfaces above and below the cell. And then there will be correction fluxes, which we'll call g tilde, which are based on second derivatives in y that can be calculated in exactly the same way that we calculated the second derivatives in x when we calculated the f tilde correction terms. But there's one new wrinkle here, and that is that these correction terms, in addition to modeling those second derivatives in x and second derivatives in y that are a natural generalization of the 1D algorithm, there's also this mixed derivative qxy, and these correction fluxes, the f tildes and the g tildes, will both come into play in adding in approximations to the cross derivative term that are really needed in order to get second order accuracy with a method in 2 space dimensions. So let's look first at the upwind method and start out with just the what's called the donor cell upwind method sometimes, the sort of simplest version of Godunov's method on a rectangular grid in 2 space dimensions, where we simply In the x direction, we solve the Riemann problem in x by updating q by u plus times qij minus qi minus 1j. That would give some wave that's moving in from the left edge of the cell. And then we would also have u minus times qi plus 1, j plus 1. In the picture here, I'm assuming u is positive, so there wouldn't be any cell coming in from the right edge. And so that term in this case would be 0. But then we'll also add in corresponding terms in the y direction. So if v is positive, then v times the jump in q in the y direction would correspond to this wave that's moving upwards from the bottom boundary. And in this particular case drawn here, the v minus would be 0, and so that term wouldn't come into play. So this would be kind of the simplest possible generalization of the upwind method to 2 dimensions, just solving the Riemann problem at each cell and looking at how those waves come in to each cell, and without adding in any sort of second order correction terms yet. But already we see that there's a potential problem with this approach, and that is that these 2 waves that are coming in are sort of overlapping with each other. And it turns out that you can show that this method is stable only if the sum of the u delta t over delta x and v delta t over delta y, which are sort of the Courant numbers in the x and y direction separately, only if the sum of those is less than or equal to 1 do you get a stable method in 2D. And that's because these waves are sort of overlapping with each other, and they're not really behaving in the proper way, because really information should be flowing along characteristics in the direction specified by this uv vector. So there's a simple way to improve the donor cell upwind method. It's still only first order accurate, but it's stable for larger values of the time step often, and it does a better job of moving information in the correct direction. And that is to take these discontinuities, for example, the discontinuity of the left boundary, and recognize that it should really be moving in the direction uv by distance determined by the time step. And so that wave should really be overlapping not just the cell to the right of the interface, but also the cell up above. And similarly, when we solve the Riemann problem between the cell below and this cell, that wave should also be moving at some angle to the grid. And so that wave should also be affecting not only the cell immediately above, but also this cell over here to the right. And so when we update the cell averages, in addition to using this wave to update the cell here by a certain amount, there's also this sort of triangular portion that should be used to update the cell above. But if you look at how all of these waves sort of fit together, and similarly we would have waves coming from the next cell down here, we'd have this set of waves that are drawn here. Those would also sort of fit together. And you can show that if you do this and transport things according to this corner transport upwind, the new cell average you get in this cell will be exactly an average over this shifted cell, which is shifted exactly along the characteristics, and it is really the average over this shifted cell that we would like to use as our new cell average within the cell. So putting together these sort of wave propagation ideas with the waves propagating in the correct direction and updating all of the cells that they influence gives you a method that does a better job of representing the simple situation here for advection, where the true solution is shifting at some angle to the grid, and we want to just average that shifted solution back onto the grid. And now you can show that this method is stable if the maximum of u delta t over delta x and v delta t over delta y is less than or equal to 1. So that would allow waves to go all the way. We could take a time step in this case that was large enough that it went up to here. Once one of these waves starts to move into the next cell over, then we have to stop. But we can at least take a larger time step. Typically, if the wave is moving at some angle to the grid, then what's allowed in the donor cell upwind method. So this corner transport upwind method, as I said, we can think of it as propagating the wave into the adjacent cell as the upwind method would, but then there's a little triangular area here that we really want to transfer from the cell it originally went into, which is this little area down here, and instead it should be moved into the cell up above. And one way to accomplish that is to figure out what's the area of that cell and the mass that's carried by that wave times that area. That amount should be updating this cell average up above rather than the cell average down below. And so even though we computed this wave by solving a Riemann problem in the x direction originally, we can look at that transfer from this cell to the cell up above as a modification to the G tilde flux, which is the flux at the top edge of that cell. So the area of that little triangular piece is the area of a triangle, 1/2 the base times the height, which are u delta t and v delta t, and the jump across that wave, that's being transported is just the jump in q, and then we're moving it this distance, or it's covering this area 1/2 u v delta t squared, but then we're averaging it over the full grid, which has size delta x times delta y. So this ratio is the fraction of the cell that's covered by that little triangular piece of the wave, and this is the jump in q across that wave, and so that's the amount that we should be adding into the cell up above and subtracting off from the cell down below in order to correct things. And so that can be accomplished by specifying this interface flux at the top of the interface, because when we do the flux differencing, that will be added into one cell and subtracted off from the adjacent cell. And another way to look at that is, as this little area comes up here and is affecting this cell, also when we solve the Riemann problem in the cells down below, which is this Riemann problem here, there will be another little triangular area that's also affecting this cell, and that will be affecting the G tilde flux at the bottom of the cell, whereas before we were looking at an effect on G tilde at the top of the cell. But then when we do the flux differencing, that differencing these values between the top and the bottom of the cell, multiplying by delta t and dividing by delta y in the flux differencing formula, sees that we're really getting an approximation to exactly this cross derivative term, 1/2 delta t squared u times v times the cross derivative qxy. And remember, this was one of the terms that comes into the Taylor series expansion for the solution at time delta t later. We had 1/2 delta t squared times u dx plus v dy squared times q comes into the Taylor series. And that gives us not only u squared times second derivatives in x and v squared times second derivatives in y, it also gives us this u times d by dx multiplied by v times d by dy. And that's how this particular term is being approximated. There's also similar terms when we look at the updates, the modifications that are made to the F tilde fluxes when we solve this Riemann problem and this Riemann problem, and those also add another term that models the v dy times u dx in this cross product term. And then to extend this from just the scalar advection to a system of equations, we can look at how we do the splitting of the matrix A in one dimension. The basic upwind method in one dimension we could write in this form, where the A plus matrix comes from taking A, doing its eigenvalue decomposition, and then splitting that up into lambda plus is the diagonal matrix with only positive eigenvalues, the others zeroed out. Lambda minus is the diagonal matrix with only the negative eigenvalues. And these two matrices are how we define A plus and A minus. And then the upwind method could be written in this form, which is a direct generalization of what we just saw for the advection equation. Instead of u plus and u minus, we have now A plus and A minus. But in one dimension, this is equivalent to diagonalizing the system and then applying the upwind algorithm on each component and then recombining. In 2D, though, we'll be looking at adding to this also the corresponding terms in the y direction. And when we do that in 2D, again, when we look at the Taylor series expansion, we have these products A times B and B times A that come in and are multiplied by cross derivatives. And we'll use this splitting of A and the corresponding splitting of B to take these matrices and split them up into AB, for example, into 4 different matrices that correspond to information that's going in sort of the 4 different directions, to the right and upwards, to the right and leftward, downwards, and then to the left and upwards or downwards. And again, for scalar advection, only one of these 4 terms is non-zero in each product depending on the sign of u and v. But for the system case, like in acoustics, you have waves going in both directions in both x and y, and so all of these matrices come into play. So here's sort of a picture of how this decomposition works. If we're solving Riemann problems in x at some interface, then at this interface we would solve and we would compute the waves going to the left and the waves going to the right. And if we multiply each wave by its wave speed and sum those up, that gives us the fluctuation A plus that's affecting the cell on the right and the fluctuation A minus that's affecting the cell on the left. And then in order to extend this to 2D, we want to do exactly the same thing we did in the scalar case a moment ago and take into account the fact that this information, some of this information should really be also moving upwards or downwards. And so we can do that by taking, for example, the A plus delta Q and splitting it up into B plus times A plus delta Q and B minus times A plus delta Q, which are the sort of upward and downward going components of A plus delta Q. And similarly, on the other side, we can take A minus delta Q and split that up into what part of that is upward going, B plus A minus delta Q, and what part is downward going, B minus A minus delta Q. So multiplying by these matrices, again, remember, just means we're doing an eigendecomposition and then summing up only the positive eigenvalues times the corresponding eigenvector, or only the negative eigenvalues times the corresponding eigenvector to take the portion of that eigendecomposition that's moving in the desired direction. And when we do this, what we see is that all of these waves, for example, maybe the B minus A minus wave that's coming down in this direction, that we can look at as first updating the cell average to the left in the usual way based on the one-dimensional algorithm, but then there's this little triangular area here that should be transferred from this cell up here down to the cell down below, which can be accomplished by means of the G tilde flux at the interface between those cells. And similarly, each of these waves can be viewed as an update to one of the G fluxes, and they're all based on the area of some triangle, depending on the speed at which these waves are going and how much they go into each of the neighboring cells. So this picture isn't exactly right. This isn't really what would happen in a two-dimensional problem, but it's sort of a good approximation to what goes on. But to sort of illustrate what really would happen at an interface like this, if we have a two-dimensional equations like acoustics, this next slide is supposed to illustrate or give an idea of what might happen at an interface if these were 4 cells here. In this case, I'm taking just one cell, the one colored in red here, where the pressure is 4 in the acoustics equations, and in all 3 of the other cells, the pressure is 0, and U and V are 0 everywhere. So just to keep things simple for this illustration, assume that we just have this situation, and also that all of our material parameters are equal to 1. If rho and k, the bulk modulus, are both 1, then so are the sound speed and the impedance. And in that case, we can easily look at how each of the solutions of these one-dimensional Riemann problems looks. So at this interface, we have a wave that's moving to the right at speed 1 and a wave that's moving to the left at speed 1. And the eigenvectors in the x direction. In terms of pressure u and v, the eigenvectors are minus 1, 1, well actually the eigenvectors are, say, minus 1, 1, 0, and 1, 1, 0 for the left-going and right-going eigenvectors, and there's no jump in the vertical velocity v across either of the eigenvectors. And on the other hand, in the y direction, we have waves that are going upward and downward, and the corresponding eigenvectors now have jumps in v but not in u, so the eigenvectors are like minus 1, 0, 1, and 1, 0, 1. And so you can easily work out that in each coordinate direction, the solution, if we stay away from the corner at least, the solution is that you end up with two waves, and in between the two waves, the pressure has the value 2, halfway between 0 and 4, and the velocity is also equal to 2, the velocity in the direction of propagation. So in this region, u is equal to 2, and in this region up here, v is equal to 2. And in this corner region, these waves don't exactly linearly superimpose, or at least not outside of a circle that's centered at the corner. The information about what's going on at the corner spreads out isotropically in all directions if we really solve the Riemann problem correctly. So outside of the circle, these two sort of plane wave solutions is correct, but inside the circle, something else happens near the corner. And it's that something else that's happening that we're approximating with these transverse waves that are now being used to transfer information to neighboring cells. But what we're doing with those triangular waves is not really the correct thing, so I just wanted to show you what it would look like more correctly for this very simple case. So this is how the solution actually involves here. And here the color represents the pressure, so we see this region in between the waves where the pressure is 2, and either u is 2 or v is 2 in between the waves in the two different directions. The colored contours here, contours of u are in blue, and the contours of v are in green. So you can see that there's a jump in u across this wave and this wave, a jump in v across this wave and this wave, and we have these two sets of plane waves. And again, outside of this circle that's expanding at speed 1 from the corner, the superposition of these two waves is the correct solution. And when you add these two waves together, you get 0, for example, in this little white region down here. But inside this region that's influenced by the corner, the solution is more complicated. And again, contours of the velocity vectors are shown there to sort of show you that you end up with something that's actually sort of isotropically expanding away from the corner. So in our finite volume method, using these transverse waves, we're essentially approximating what's going on in this circular region by using this wave that's propagating to the right, but then also propagating it up in this direction. And similarly, this wave that's propagating upwards, we would also be propagating part of it after we do the eigendecomposition in the transverse direction in this direction. So we would be getting different values in these cells coming from the waves, the transverse propagation of these waves. And similarly, there would be waves that would go in other directions. And so in this square region, sort of around the corner, we would be modifying things according to that set of triangular waves, which again is not the exact solution. But on the other hand, once we average that sort of solution onto our grid cells again at the end of a time step, it turns out to give a reasonably good approximation, even in a case of a system where it's not the exact thing. Again, for scalar advection, it would be a simpler picture, and those waves would be correct, but not for acoustics. And if we go to a nonlinear system, well, then things become much more complicated. So for example, this is one of the examples that's in the Clawpack gallery, the Euler 2D quadrants example. This is one of a large set of test problems that was proposed back in the late 80s to test two-dimensional numerical algorithms where you take 4 quadrants with 4 different values in the different quadrants. So one value, one vector here, another here, here, and here. And so that you have just 4 Riemann problems away from the corner again. And in this particular example, I'll show the data is chosen so that this interface here, for example, gives just a single shock wave moving to the left. This interface gives a single shock wave moving downward. So the solution of the Riemann problem has just one non-zero wave in each of those cases. And similarly also for these two. So that away from the corner again, the solution is very, very simple. You just have one wave moving from each of these Riemann problems. But again, in this corner region, things will become much more complicated in the nonlinear system case. And this is for the full Euler equations of gas dynamics. And what you see is something that evolves like this. And what you're seeing here is that in addition to these waves that are moving along, here we saw a shock wave moving from this initial location roughly over to here, but it's interacting with these other waves in such a way that it gives rise to a set of shock waves and also contact discontinuities. In fact, these waves along here and everything that's going on here and here for the most part are really contact discontinuities where the pressure is constant. If we plot the pressure instead of the density, it looks more like this. And so this line, for example, is a contact where there's really a strong shear flow along here. Now, because we're using a numerical method that has some numerical viscosity, that contact discontinuity, that shear line actually rolls up. You get a Kelvin-Helmholtz instability forming, and so that's why it doesn't look like a nice linear discontinuity. Instead, you have this roll up here. But that's, in this case, sort of a numerical artifact, and it depends very much on which limiter you use, for example, how much and how fine a grid you use, exactly what sort of structures you get in these sorts of solutions. Also, when you look at the pressure wave, the pressure should be identically constant along that line, but you can see sort of low pressure regions in the centers of these vortices that have formed where the pressure is lower than it should be because of the swirling flow. So that's just one example of how complicated these solutions should look. In all of these, both of these cases, this one and also the one we looked at here, the solution has the property, the exact solution has the property that it's actually self-similar in time. As time advances, it's really the same pattern that's just expanding outwards. And that should be true here too, that you should see exactly the same figure. If we zoomed in here on a very small region and blew it up, that should in principle look exactly like what it looks like here at a later time. It won't exactly because of this roll up of the slip lines, but if we were really solving the inviscid Euler equations exactly, that's the sort of pattern that you would see. So these sorts of examples are nice test problems for numerical methods. They're easy to set up and they have simple boundary conditions because we just have a shock that's propagating along the boundary. And so extrapolation boundary conditions, for example, work very well here, at least until things start to leave the boundary. So they're nice test problems, but they also show how difficult it would be to try to develop a full, say, two-dimensional Riemann solver that actually takes the interface between 4 grid cells and tries to do the right thing at that interface. You might hope that you could do an extension of the 1D Riemann solver to 2D by looking at arbitrary sets of data in 4 neighboring points at a corner and figure out what's the right solution. And there have been some attempts to do things in that direction, but they tend to be very expensive and not necessarily all that much better than using one-dimensional Riemann solvers and some of these other ideas like transverse solvers to approximate what goes on in 2 dimensions. So I won't say too much more about it except to mention what is used in Clawpack. In the Clawpack software, we have what we call a normal Riemann solver that solves the Riemann problem orthogonal to each grid interface, either in the x direction or the y direction. And there's a parameter that gets passed into this RPN2, the normal Riemann solver routine, that's called IXY, that just tells whether you're solving it in the x direction or the y direction. So typically it's very similar formulas. If it's an isotropic system like acoustics or gas dynamics or shallow water equations, what you do in the x direction and the y direction are essentially identical, except you use a different component of the velocity. And so they're combined into a single Riemann solver with this parameter that tells what direction you're doing things in. And that Riemann solver is exactly like the 1D Riemann solver, that it would take the jump in Q and split it up into fluctuations A plus delta Q and A minus delta Q based on eigenvalues of the matrix A and just looking at the one-dimensional problem. Or, depending on the value of x, I, x, y, it may be the one-dimensional equation in the y direction and the eigenvectors of B that would come into play instead of A. And if you're doing dimensional splitting, then that's the only Riemann solver that you need to provide for Clawpack. And it's often essentially the same as the one-dimensional Riemann solver for the same system of equations. So that makes it relatively easy to go from 1D to 2D. If you want to use these more complicated wave propagation methods that also take into account the transverse solvers, then there's a second set of Riemann solvers, or second Riemann solver for your problem, that's called the Transverse Riemann solver, RPT2. And what it does is it takes the output from RPN, so either A plus delta Q or possibly A minus delta Q or B plus delta Q or B minus delta Q, takes one of those fluctuations and it splits it up in the transverse direction, the orthogonal direction. So if what came in was A plus delta Q, then it would split it into B minus A plus delta Q and B plus A plus delta Q, the part of that right-going fluctuation in X that is going downwards or upwards in the Y direction. And that would be done by splitting A plus delta Q into eigenvectors of B. Or conversely, it might split B plus or minus delta Q into eigenvectors of A if we started with Riemann problems in the Y direction and now we're doing the transverse Riemann solver in the orthogonal direction to that. So the way that the subroutine is actually written, this RPT2 takes as input something called AS dq, which is supposed to represent A star delta Q, where the star can be either minus or plus, and there's another parameter that gets passed in, this IMP, that has the value either 1 or 2 to indicate whether AS dq represents the left-going fluctuation or the right-going fluctuation. And then it returns B minus A star delta Q and B plus A star delta Q. So this transverse Riemann solver has to be called twice. So if we're doing things in the x direction, for example, we would first calculate A plus delta Q and A minus delta Q, and then for each of those we would call RPT2 to split it up into the upgoing and downgoing parts. That would be one call to RPT2, and then starting with the left-going wave, another call to RPT2 would compute the upgoing and downgoing parts of that wave. And then when we do our sweeps in the y direction, we would also have to take each B plus delta Q and B minus delta Q and split those up in the transverse direction using eigenvectors of A. But all of those splittings are done by the same routine RPT2 that takes this IMP as one of its parameters. And as I said, it also takes the parameter IXY, which tells what direction the original solve was in. And so we have two parameters that tell what direction the original solve was in, and now whether we're looking at the left-going or right-going waves, or if the original direction was y, then whether we're looking at the upgoing or downgoing waves. So just as one quick example, if we're looking at, say, gas dynamics to show how it's relatively easy to go from 1D to 2D even with these transverse solvers, these are the equations of gas dynamics in the case where the pressure is just a function of density. So isothermal or isentropic flow, for example, and we don't have an energy equation, but it's not too much more complicated if we did. For these equations, if we're looking in the x direction, if that's where we're doing our initial set of Riemann solves, then the equation that we're solving is just the qt plus fx equals 0 part. And that means we just drop off all the y derivatives from here. And what we end up with is the first two equations are exactly the 1D equations for this system of equations. And then it's augmented with the third equation here, which is really just an advection equation for the vertical velocity v. So we're really just solving the nonlinear Riemann problem in the x direction for rho and u as a 1D solver would do. And then there's an additional contact discontinuity in the solution that moves with speed u and represents any jump in the vertical velocity v, which simply moves with the flow. And similarly, if we're solving the 1D equation, the Riemann problem in y, then we'd be looking at qt plus g of qy equals 0, so we'd be dropping all of the x derivative terms. And then we have equations where the first and third equation really just look like the one-dimensional equations for gas dynamics, but where the velocity now is v, the upward vertical velocity. But otherwise, those have exactly the same structure as the one-dimensional equations. It's just with v instead of u and y instead of x. And then it's now the middle equation that represents an advection equation for any shear velocity in the u direction that gets advected with this vertical velocity v. So exactly the same Riemann solver can be used as for the other case. We just have to switch which component of the velocity we're working with as the one that comes into the 1D solver and which one is simply advected with the flow. And then if we want to add in a transverse Riemann solver, we need to figure out what eigenvectors do we split things in the transverse direction. And if, for example, we're using a row solver for our one-dimensional solver in the x or y direction of the sort we just talked about, we would often use an approximate Riemann solver like a row solver. Then remember, the row solver solves a linear system of equations where we have instead of qt plus f of qx equals 0, we use qt plus a hat qx equals 0, where a hat is some approximation to the Jacobian matrix. It's actually the Jacobian matrix evaluated at q hat, where q hat is defined by the average value of the density, but this special average, row average of the velocity vector using the square root of the density as weighting functions. And that, remember, has nice properties. And so we can look at solving the nonlinear Riemann problem approximately by linearizing and using the eigenvectors of this Jacobian matrix. Now, if we want to take the resulting a plus delta q and a minus delta q that come out of this, which should really be written maybe as a hat plus delta q and a hat minus delta q that come out of using this Riemann solver, and we want to split them in the other direction, then what matrix do we use for the eigenvalues in the other direction? Well, since we've got these averages, q hat, we can use them to also define an approximation to the Jacobian in the other direction. So in fact, we can just take b hat equals to the g prime Jacobian matrix evaluated exactly at the state q hat that we used in doing the normal Riemann solve. And we know explicitly the eigenvalues and eigenvectors of that matrix. They're essentially the same as in the x direction. And so we can use that to split up either a minus delta q or a plus delta q into eigenvectors now of this b hat matrix, and that would define our transverse fluctuations. So there's a number of different both normal and transverse Riemann solvers available in the Riemann repository, so you might take a look there and examine some of those solvers to see how they're constructed. And then finally, let me just mention that this sort of approach to doing wave propagation with transverse solvers extends fairly naturally to a more general quadrilateral grid. You could do it on other grids too, but in particular for a quadrilateral grid, if you have some grid mapping from a logical rectangular grid to some mapped grid, maybe polar coordinates or something else, then you can extend these ideas, and the idea here would be then that at each interface, you solve a Riemann problem normal to the interface first. And that gives you waves which update the neighboring cells. Although even without doing anything in the transverse direction on a mapped grid, those cells might have some portions that are already overlapping some neighboring cells, or maybe some gaps where there's less of it than usual going into this cell. But you can figure out from the normal Riemann solve, you can use that to update the cells on either side, and then we can apply the same idea of transverse solves, where now we look at the directions that are orthogonal to the neighboring cell interfaces. So to get this, for example, the wave that's going to the right and downwards, we would look at the wave that's going to the right as being orthogonal to the original interface, but then we would solve or use eigenvectors of a matrix that's rotated in the direction that's orthogonal to this interface below the cell to figure out how much of that wave goes from this cell into the cell down below. But the nice thing about this is that when you do that, the sort of areas that you have to worry about here are still just little triangular pieces, and you can easily calculate the areas of those triangles based on the speeds at which things are moving in the normal and transverse directions. And for equations of the sort we've mostly been looking at that are isotropic, gas dynamics, shallow water equations, acoustics, etc., you can rotate the equations into any coordinate system. That was our definition of hyperbolicity. Remember that it rotated in any direction. It should still be diagonalizable, and we found that the eigenvalues and eigenvectors in an arbitrary direction could typically be written down very easily. And so you can extend these methods to any of those systems on quadrilateral grids quite nicely. So again, there's a few examples in CLAWPAC. In particular, there's advection on a 2D annulus. This example here in the CLAWPAC gallery. If we go to plots, I think this was actually done with adaptive mesh refinement. So the region was an annulus between two concentric circles, but the grid it was being solved on was a polar coordinate grid in that region. So the radial coordinate was going between one value and a different value, and then theta was going between 0 and 2 pi with periodic boundary conditions in the theta direction. And the solution that we were looking at is sort of a Gaussian, a positive Gaussian over here, and a negative Gaussian over here, and a varying velocity function that corresponded to solid body rotation, so that the solution should simply rotate around in this annulus. And the grids using adaptive mesh refinement follow that rotation. So here we're just showing the coordinate grid cells on the coarsest two levels, and then these white patches are a third level of refinement where the grid cells aren't drawn, but they're following the region, these Gaussians. Away from the Gaussians, the solution was constant, and so you don't really need a very fine grid, but in those regions you do. But this was done using exactly the same sort of finite volume method with these transverse solvers, but on this polar coordinate grid. And here's just another picture with contours of the two Gaussians as they rotate around. So there's a chapter in the book, chapter 23, I guess it is, that discusses extensions to quadrilateral grids in more detail, but the basic ideas are quite similar to a Cartesian grid.